Now we want to talk about the Picological dimension of subgroups. Let H be a closed subgroup of a proof-finite group G. Then, as expected, the Picological dimension of H is at most that of G. And equality happens if and only if the index of H in every finite quotient of G is prime to P. In particular, this means that the Picological dimension of G is just going to be equal to that of its pro-P Sylow subgroup. Thus, this reduces the computation of Picological dimension of any proof-finite group to that of the pro-P groups. So in the next video, we're going to talk about the Picological dimension of pro-P groups. But for now, let's prove this statement. So let's assume that the cohomological dimension of G is equal to n, right? And we want to show that the Picological dimension of H is less than or equal to n. Well, by definition, this would mean that for every I greater than n, and for every continuous H modulo B, we should have the P primary torsion part of this cohomology group vanishes. But by hypothesis, we know that the P primary torsion part of these modules vanishes. So how do we relate the cohomology of H with the cohomology of G? Well, the canonical tool for this is Shapiro's lemma. From an H module B, we can construct a natural G module, which is the co-induced module, and Shapiro's lemma gives us that the following cohomology groups are equal. So then the P primary part must be equal, and thus we see that the P primary part of these modules must be 0. So we have that the P cohomological dimension of H must be less than or equal to that of G. Now it remains to discuss when equality holds. And sorry, it's not an if and only if, it's just sufficient. So let us show that if the index of H in every finite quotient of G is prime to P, then we must have the two cohomological dimension must be equal. So this actually comes from the following corollary of this proposition about the co-restriction composed with restriction map. So let us first show how this corollary implies that in this case the cohomological dimension of H and of G are equal, and then we'll explain how we get this corollary. Alright, so the corollary said that if the index of H in every finite quotient of G is prime to P, then the restriction map is gonna be injective on the P primary torsion part. So why does this imply the two cohomological dimensions are equal? Well, this would mean that whenever this module vanish, then this one must also vanish. So that means that the cohomological dimension of G must be less than or equal to the cohomological dimension of H. So combined with the previous part, we must have that they must be equal. Now we explain how we get this corollary from this proposition on the co-restriction restriction map. So the proposition says that this composition is just going to be equal to the multiplication by the index of H in G. In particular, if this index is M, then this map must be injective on the prime to M torsion part. So why is that? Well, let A be a cocycle in Hi of G, A that lies inside the kernel of this map, right? What does that mean? That would mean that MA is gonna be 0. Now this would mean that the order of A must divide M. So if A lies in the prime to M torsion part, if the order of A is prime to M, then the only possibility is that A must be 0. So the restriction map must be injective on the prime to M torsion part. Alright, so that's the proposition. Well, we don't have this yet, the corollary from this. Actually, we do not want to apply this for the proposition in the case when this H is our group H here. Rather, to prove that this map is injective, we want to look at review the definition of this restriction map. Remember, these groups, these cohomology groups, are just defined to be the direct limit of these systems. So the restriction map was defined to be induced by the following restriction maps. So let's say there is some element in here that maps to 0, right? We want to show that A is 0. Because this cohomology group is a direct limit of this system, A must comes from one of these, and we can shrink U alpha enough so that we can assume that A maps to 0 here. Now we will apply the proposition before this group, right? Now the index of this group inside the quotient is prime to P. So by the proposition, we must have that this restriction map must be injective on the P primary torsion. Thus we get that if the index of H in every finite quotient of G is prime to P, then the restriction map is going to be injective on P primary torsions. This means that the cohomological dimension of H is greater than or equal to that of G, and so that means that the cohomological dimension of H must be equal to that of G.